In today's video, we are going to try to prove conservation of energy from the point of view of particle physics. Now, in particle physics, we generally denote the change of state as being the destruction of one state and the creation of another. For that, I'm going to use a creation operator, which I'll denote here as psi plus, and an annihilation operator, just psi. Psi plus is going to be equivalent to this sum right here. And recall that omega is a proxy for energy and K is a proxy for momentum. With psi plus the creation operator defined, let's also define the annihilation operator. Very similar. Don't worry quite about exactly what the symbolism means yet. It'll become apparent as the equations are mapped out. Operators are for creation and annihilation, as I said. So if we're going from one state here, or moving up this way, we can call that a state. And we can call this later state with some interaction here as this, in this space right here, this first state is being destroyed and is creating the second state. All right, that's the basic concept behind this. For these two field operations, the creation and annihilation, let's now consider particle scattering in spacetime. For this, let's draw a spacetime diagram. And for ease of this, just to make it simple, let's denote this position as x equals 0, where our interaction will be happening. So our states, we're switching from state k sub I to state k final, right? K sub I is your initial state. And recall that k is a proxy for momentum. That will be important when we're proving conservation of momentum in the next video. Now, for these states to actually happen, we have to integrate over time because the time isn't set on when this will happen. Now, in actuality, there's a G term out here called the coupling constant, but for all intents and purposes, we can just ignore it. I'm not going to include it in here, it's just a number. Now, our operation when fully expressed is going to look like this, where we can expand using the full terms for the operators seen here. Okay, sorry about that. Okay, so now that we have it written out like this, we can do the inner product. If you recall, the inner product gives us a probability amplitude of an event occurring. And we simply write it like this. Recall that this value here, the components are actually going to be complex conjugated when transferred to a row vector rather than a column vector. But we can write the rest of the term the same as before. Just like that. And remember, we're doing inner product, so you need to have the initial state out here too as a cat vector. Okay, so now let's define something that is pretty essential to this understanding. the creation operator, or sorry, the field operator for creation, psi plus, a part of it that resides here, this component right here, we'll call this 1, and we'll call this other component 2. When the first one acts with the bra, K sub F, you get a vacuum state bra. Which we write is just a bra 0. And then the second term acting on the initial state in the ket vector gives us a vacuum state there as well. Let me fix that K. Looks wonky. Close up. All right, so then we can rewrite this with these terms simply substituted in. Review the vacuum state, integrating over time. And then there's one thing that we have to take into account. Since the creation operator is this entire first bit here, and the annihilation operator is this entire second bit here, these K's in the first one and the omegas in the first one are gonna, in the first one are gonna have to be denoted with F's to show that they were acting on that state. They're part of that state. So we just simply write in K sub F here. Everything's the same though. Now they just have corresponding states. And then with the second one, it's just with the initial. All right. Now, we can actually take out the bra and ket, do an inner product of 0 with 0. As we know, an inner product of anything with itself is simply going to give us 1. So we can ignore that term and rewrite the whole thing as the integral of this term. You may realize what's about to happen if you're familiar with calculus and Euler's identity. All right. So next, we can, since we defined x as 0, we can simply plug in that value and simplify this equation. So this one's negative here. All right. Now, these two can simply be added together, which gives us, or when I say added together, I mean these, the exponents can be added together since we're multiplying by the same base. So that will yield and for those of you who are familiar with Euler's identity, this is going to be equal to cosine alpha x plus pi sine alpha x. And since it's a combination of sines and cosines, and we're taking the integral of it, the integral of a linear combination of sines and cosines, such as this, over time, is always equal to 0. Therefore, the only way in which any meaningful value can be attained from this is if it were no longer a combination like this, which means this would have to be true. which would mean omega f minus omega sub I equals 0. Because in this case, this becomes the integral of e to the 0th power, which we can actually just simplify and write as 1, which is easier. There's other things that are going to be in here that I didn't include, such as the coupling constant, but the general idea is that no proper solution can be attained unless omega sub f and omega sub I, when subtracted, are equal to 0. And from this, we could say that omega sub f equals omega sub I. So the final omega equals the initial omega. And if you recall, omega was a proxy. Oops. Omega was a proxy for energy. So if we multiply the reduced Planck constant on both sides of this equation, which, for those of you who don't know, reduced Planck's constant is just a regular Planck's constant over 2 pi. Now, multiplying the reduced Planck's constant on both sides, we could say that the final energy equals the initial energy, which means that in transitions of states, energy is conserved. Therefore, this can be considered a proof of conservation of energy. Thank you for watching.